Now, between elliptical and spiral galaxies, Hubble introduced the immediate type S0s, which are galaxies that obviously had a disk, but he couldn't see any spiral arms. Here is Sombrero Galaxy, one of the famous examples. And indeed, physically, they are transitional in that sense that it's a large bulge with relatively small, or rather unimportant disk, and disk that doesn't have a lot of active star formation. And just like other spiral galaxies, these S0s, or lenticulars, because their shape resembles a lens, could also contain bars. Among the spiral sequence, which really is two parallel sequences, one with bars, one without, there is a trend from earliest types, SAs, to the latest types, SCs, sometimes people call SDs in even more extreme cases, in the sense that as you go along that sequence, the bulge becomes less important, the disk becomes more important, spiral arms become more prominent and more ragged as you go further. Here is a typical spiral galaxy, our immediate neighbor, Andromeda Galaxy, or M31, which has two big companions, M32, small elliptical, and NGC 205, which is so-called dwarf elliptical, as well as a lot of even smaller companions, dwarf spheroidals. Now, in this picture, all of the little dots that you see are actually stars in our own galaxy. M51 is another well-photographed spiral galaxy. It seems to have something at the end of its spiral arm. This is actually another galaxy with which M51 is interacting, sort of its own Magellanic Cloud, except bigger and in a more spectacular state of merging. So about half of all disk galaxies contain these bars, and including Milky Way. Ours is hard to see because of the dust in the disk, but now, thanks to the infrared observations, we are pretty sure that we do have a bar. And what bars really are, they're a form of dynamical instability in rotating disks that forms spontaneously. Presence of dark halos actually can regulate against formation of bars, so spiral disks are just borderline unstable to formation of bars. Now, bars are not static patterns. They actually do rotate as the disk rotates, unlike spiral arms, which really are not. They're density waves rather than distinct physical subsystems, about which we'll talk about later. Bars can also serve as a means of transferring gas from the outer disk to the middle, where it can ignite star formation or feed an active nucleus, if there is one. The reason for this is that this rotating triaxial potential creates instability and can soak energy or angular momentum of the surrounding interstellar medium, feeding it to the middle. You see, often spiral arms seem to originate at the ends of a bar, and that too has to do with dynamical instabilities and mechanisms of formation of spiral arms. And then there are dwarf galaxies, which is something of a heterogeneous grab bag of things. Hubble put them at the end of his sequence, but really there are several completely different families in there. Dwarfs can be gas-poor or gas-rich. Gas-rich would be things like very small spirals or genuinely galaxies with no specific shape, but plenty of gas igniting star formation. That, by and large, unless they have a lot of star formation, they have very low surface brightness, and so they're very hard to spot. And just like the majority of all stars are dwarfs, the majority of all galaxies are also dwarfs. Numerically, they're more important than traditional galaxies of the Hubble sequence, but they actually don't contain very significant amount of mass or luminosity. So you can think of these dwarf galaxies as food for larger galaxies. They keep merging into the bigger ones, and even in halo of Milky Way, we now see remnants of at least one dwarf galaxy being consumed through a tidal interaction, the so-called Sagittarius dwarf. Dwarf galaxies themselves are probably not the product of any significant merging of even smaller pieces. In some sense, they are sort of the original building blocks of larger galaxies. So here is what Hubble called a dwarf irregular. This is the Large Magellanic Cloud. It does look a little bit irregular, but actually what it is a dwarf barred spiral in process of tidal disruption interacting with Milky Way. and the obvious part is the bar. There are also generally young star-forming dwarf galaxies. One Zwicky 18 from Zwicky's catalog is shown here. You can think of them as almost like puddles of gas, which are just beginning to form stars for the first time, or at any rate, they haven't formed many stars in the past. So these are the closest thing to young galaxies that we see near us. Now, what Hubble thought as dwarf ellipticals or dwarf spheroidals are a completely different kind of beasts. There are small ellipticals, let's scale down versions of big ellipticals, and that's a separate story. M32 is an example of those. But even among the dwarfs, there seem to be two classes of things. One is dwarf ellipticals, which really are probably a different family of objects altogether, and dwarf spheroidals, so-called because they belong to the galactic halo. Usually they do have ellipticity, and those look just like a little peppering of stars atop of the background. They do not contain much in terms of stars, but they turn out to contain a lot of dark matter, and they're interesting from that viewpoint. More recently, thanks to the more sensitive detectors, it was realized that there are a lot of spirals out there which have very, very low surface brightness disks, but nevertheless, they do have disks. And the question was, how many of those did we miss? Those are icebergs in the sky that you just see the bright central portion, but not the disk, which you really have to work hard to pull out of the noise. And the interesting thing about these galaxies is that they seem like normal spiral in any other way, in terms of the amount of gas, in terms of rotation curves, total masses, and so on, except they haven't made many stars in disks. And the reasons for this are still unclear. One of the first large but low surface brightness disks called Malin-1. The two panels on the lower right show normal contrast picture and a really high contrast picture. So if you look at a distribution of surface brightness of disks, you see something like that. At the bright end, which here is on the right, are the traditional Hubble spirals. But then there is an extension to the lower surface brightness of these newly found low surface brightness disks. In the past, because of selection effect, their existence just wasn't known. They're hard to pull out of the noise. And it appeared as if there was a Gaussian distribution with a characteristic central surface brightness, and that was called Freeman's law. So this again turned out to be more or less a selection effect. A different kind of irregular galaxies are what we now know are really mergers of galaxies in progress, and we talked about those when we talked about numerical simulations. Here are a couple of famous examples. The antennae, you see tidal tails, and Tadpole galaxy, where again has a long tidal tail. And obviously, since they represent at least two galaxies involved, they do not fit in any of the traditional morphological bins. But we know that they're really important in terms of galaxy evolution, because galaxy merging is one of the key processes that are contributing to evolution of galaxies. A subset of those are so-called polar ring galaxies, where the merger of two spirals is not yet complete, and their angular momenta were orthogonal. So you see a ring, remnant of one of them, orthogonal to the disk of the other. This was puzzling at first until people realized what was going on. So next time we will actually look into the trends of physical measurable properties along Hubble sequence and where do they really come from.